C34 June 2017, question 12. What's not to like, really? We've got a bit of integration with substitution. There's a differential equation here. There are connected rates of change, but a lot of words, so we'll go through bit by bit. We've got this cylindrical water tank, a right cylindrical tank, which means this little sides are vertical. It's not sort of leaning over. The diameter is 4 meters. We've got a radius of 2, and the height is 2.25 meters. Water is flowing at the tank at a constant rate of 0.4 pi meters cubed per minute. There's my hose pipe with some water going in. There's a tap at point T at the base of the tank. The tap is open, the water leaves the tank at this rate, which is proportional to the square root of h, and h is the height of the water in meters. Show that at the time, t minutes after the tap has been opened, the height h of the water satisfies that differential equation. Right, now the water going in, the water going out are changing the volume, so it's going to show us the rate of change of the volume. The 0.4 pi is the water going in, so that's a positive contribution to dV over dt. It's increasing the volume, so that's plus. This one, though, the water's going out, so that's going to decrease the volume. So it's a negative contribution to the rate of change of the volume. So that's what dV over dt is in terms of h. This is constant, but this bit depends on the square root of h. And we're going to get into this form, but we've got dH over dt rather than dV over dt. So we're going to connect the rates of change by doing this. dV over dH multiplied by dH over dt is the same as dV over dt. So what we need, this dV over dH, we've got this in terms of h. So we've got this in terms of h. So we need this. The volume, though, the volume of water, well, it's the area of the base multiplied by the height. The area of the base is a circle pi r squared, which is 4 pi multiplied by the height, which means the dV over dH is 4 pi, just differentiating this. So I can write then the dV over dt, which is this for the first line, is equal to 4 pi multiplied by dH over dt. I can get rid of those pi, divide by pi, and if I multiply by 5, I actually do get this 20 dH over dt, and that'll be 1, and that'll be 2. And then it says the instant the tap is open, t is 0, h is 0.16. Use the differential equation to show that the time taken is to a height of 2.25 for a time for it to fill. Really, it's given by this. So if I separate the variables, I need the h's on one side, so I'll divide both sides by 2 minus root h. I can't subtract, or I don't want to do that because I'll get a bit of a mess when I multiply by dt. So I divide by 2 minus root h. So I'll just get 1 over here and that fraction on the left-hand side. I'll put the dt up here, and then I'll be integrating both sides. The left-hand side, well, I want to integrate, find the time it takes to go from 0.16 to 2.25. So I'm going to integrate the h in between 0.16 and 2.25. That's going to correspond to the time of 0 and a time when it's full, which I call big T, not this T, not the tap T. It's the time it takes to fill. And this right-hand side will just be the time, because if I integrate 1, I just get little t. So it'll be little t with t and 0 substituted. So this will give me the time it takes to fill up. And then using the substitution, h equals 2 minus x squared. I don't know what the otherwise is. Find the time taken to fill the tank to a height of 2.25. Give your answer in minutes to the nearest minute. So here's my substitution. I want dH. If I differentiate the h in terms of x, the 2 will go in front. Then I'll have 2 minus x to the power of 1, but then I'll have a minus in front because that's what I get when I differentiate the bracket. Or if you like, dH is minus 2 times 2 minus x dx. So looking at the integral, I've got 20 on the top, or 2 minus root h on the bottom. Root h is just 2 minus x. And then I need to multiply it by dH, which is this. And my limits, well, to get 2.25 for the h, I'll need 1.5 squared is 2.25. So I need to put 0.5 in there. And 2.5 is no good because the tank's only 2.25 meters high. And the lower limit, to get 0.16 for the h, I've got a square 0.4, which is 2 minus 1.6. So if I simplify this, this bottom line is just x. And the top line is going to be 20 times this, and this is minus 4 plus 2x. So I'll have minus 80, 20 times minus 4, and 20 times 2x. To do the integral, I need to break up into two fractions. So minus 80 over x plus just 40. This is going to be an ln, of course. So minus 80 ln x plus 40x. And then I'm going to stick my limits in 0.5 and 1.6. 0.5 goes in first. And then minus the 1.6. I can do a bit of simplifying rather than put all this in the calculator. I've got minus 80 ln 0.5, and then I've got plus 80 ln 1.6. So that's the same as 80 ln 3.2, because it's really 80 ln 1.6 and then minus 80 ln 0.5. I take the 80 out, I'll have ln 6 minus ln 0.5. So I've got to do 1.6 divided by 0.5. And then the other term, I've got 20, and then minus 64 is minus 44. Stick that in the calculator, and you get about 49.